Before we dive into the deepest mysteries of our universe, I'm curious, where are you watching from tonight? Whether you're in a bustling city where streetlights paint your walls with gentle glows, a quiet suburban home where the only sounds are distant traffic and settling walls, or perhaps somewhere under vast open skies where stars shine without competition from artificial lights. I'd love to know where this journey finds you. Take a moment to get comfortable. Pull up those covers, adjust your pillow, and let your body sink into that perfect position where sleep feels just within reach. Tonight, we're going on a journey through the cosmos. Not the kind that will keep you wide awake with excitement, but the gentle kind that lets your mind wander through infinite possibilities while your body slowly surrenders to rest. So close your eyes, breathe deeply, and let's begin our journey into the unknown. Tonight, the mysteries of time, matter, and existence itself will be your companions as you drift toward dreams. Time's enigma stands among physics' most bewildering puzzles, a paradox so profound it challenges our very perception of reality. The fundamental equations governing our universe, from Newton's laws of motion to Einstein's field equations, show absolutely no preference for temporal direction. These mathematical frameworks are time-symmetric, meaning they work equally well whether time flows forward or backward, yet we exist in a world where time advances in one direction exclusively, relentlessly, unstoppably forward. When a mirror shatters, its fragments scatter chaotically across the floor, never spontaneously reassembling into a perfect reflective surface. When we drop an egg, it breaks, but we never witness the reverse, scattered shell fragments and spilled yolk leaping upward to form a pristine egg. At the quantum scale, where particles dance according to probability waves, physical laws remain completely symmetric under time reversal. An electron doesn't care whether it's moving into the future or retreating into the past. It behaves identically in either temporal direction. The mathematics governing electromagnetic interactions, the strong and weak nuclear forces, even gravity itself, all are indifferent to time's supposed direction. This presents us with what physicists call the arrow of time problem. If the universe's fundamental laws don't distinguish between past and future, why do we experience such a clear temporal direction? Why does cause precede effect? Why do we remember the past but not the future? Why does disorder increase rather than decrease? These questions probe the very nature of temporal experience and physical reality. The mystery deepened considerably in the 19th century when Rudolf Clausius, a German physicist and mathematician, introduced the revolutionary concept of entropy, a quantitative measure of systemic disorder, or, more precisely, the number of microscopic ways a system can be arranged. Clausius wasn't merely proposing an abstract mathematical concept. He was identifying a fundamental property of nature that would forever change our understanding of time, energy, and the universe itself. Consider a simple example that illustrates entropy's profound implications. A glass containing cold water possesses relatively low entropy because the water molecules are moving slowly in relatively organized patterns. Now add hot water to this glass. The thermal energy begins to distribute itself uniformly throughout the liquid. The fast-moving hot water molecules collide with slow-moving cold ones, transferring kinetic energy until the entire system reaches thermal equilibrium. This final state has maximum entropy because the energy is distributed as evenly as possible among all the water molecules. But here's the crucial insight that Clausius provided. This process is irreversible. The hot and cold water will never spontaneously separate back into distinct regions. Once thermal equilibrium is reached, the system stays there. Energy, Clausius realized, has a preferred direction of flow, from concentrated to dispersed, from organized to disorganized, from low entropy to high entropy. This observation led Clausius to formulate what became known as the second law of thermodynamics, one of the most fundamental and inviolable principles in all of science. In any isolated system, entropy always increases over time. It never decreases. This law is so fundamental that Arthur Eddington once said, "If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." The entropy increase that Clausius identified provides us with time's arrow, the physical mechanism that distinguishes past from future. Picture a perfect cup of coffee, dark aromatic liquid sitting undisturbed in a white porcelain cup. Now pour cream into this coffee. Initially, the cream creates spectacular patterns, elegant swirling eddies of white threading through black, delicate spirals and tendrils that seem almost alive in their complexity and beauty. These patterns represent a low-entropy state because the cream and coffee remain largely separate, organized into distinct regions. But this beauty is fleeting. Over time, molecular diffusion takes over. The cream molecules randomly move throughout the coffee, and the coffee molecules migrate into the cream regions. The spectacular patterns dissolve, blur, and eventually disappear entirely, leaving behind a uniform brown liquid. The system has transitioned inexorably from order to disorder, from low entropy to high entropy, and there's absolutely no going back. No amount of stirring, heating, cooling, or any other manipulation will cause the cream and coffee to spontaneously separate back into their original distinct patterns. This simple coffee cup demonstrates the arrow of time in action. We can tell which photograph was taken first, the one showing distinct cream patterns, past, or the one showing uniform brown coffee, future. The entropy increase provides an objective physical basis for temporal ordering that doesn't depend on our subjective experience or memory. Yet here lies the haunting paradox that has puzzled physicists for over a century. If entropy always increases, it must have been extraordinarily low at some point in the past. In fact, tracing entropy backward through time leads us to a stunning realization about the universe's beginning. In the earliest moments following the Big Bang, roughly 13.8 billion years ago, the universe exhibited absolutely staggering organizational precision. Matter and energy were distributed with an almost inconceivable degree of uniformity and order. The cosmic microwave background radiation, the faint afterglow of the Big Bang that we can still detect today, shows temperature variations of only about 1 part in 100,000. This represents a level of organization so precise, so incredibly fine-tuned, that it seems to balance on the edge of mathematical impossibility. To put this in perspective, imagine trying to achieve the same level of uniformity by randomly tossing coins. You'd need to get nearly identical results across billions upon billions of tosses. But why? This question strikes at the heart of cosmology and challenges our understanding of how the universe began. Why did the cosmos begin in such a bizarrely ordered state, rather than the maximum entropy chaos we might expect from a random beginning? If entropy always increases, And if the universe started in a low entropy state, what mechanism established that initial order? This puzzle has led physicists down several fascinating theoretical paths, each attempting to solve what's become known as the past hypothesis, the question of why the universe's entropy was so low in the past. Some physicists, including Nobel laureate Steven Weinberg, propose that the universe itself functions as a vast entropy-generating mechanism. As space expands due to dark energy, new regions of space-time continuously come into existence, creating additional opportunities for entropy to increase. It's like having an infinitely expanding canvas across which ink can spread. The total amount of disorder keeps growing because there's always more space to fill. This cosmological perspective suggests that entropy increase isn't just a local phenomenon occurring within fixed boundaries, but a cosmic process intimately connected to the expansion of space itself. As the universe grows larger, it creates more room for disorder, more ways for energy to spread out and become diluted. In this view, the arrow of time is directly tied to the universe's expansion. Time flows forward because space is expanding, providing new opportunities for entropy to increase. However, this explanation, while elegant, only addresses what happens after the Big Bang began. It doesn't explain the universe's initial low entropy condition. It simply pushes the mystery back one step. We're still left wondering, what established the remarkably ordered initial conditions that allowed entropy to increase over cosmic time? This is where more radical ideas enter the picture. Julian Barber, a British physicist and author of The End of Time, suggests something far more unsettling. Time itself might be an illusion, a byproduct of our limited perspective rather than a fundamental feature of reality. Barber envisions the universe not as the evolving system moving through time, but as a timeless landscape, what he calls Platonia, consisting of all possible arrangements of matter and energy. In Barber's model, what we experience as the flow of time is actually our consciousness moving through this static landscape of possibilities. Each moment, each now, exist permanently as a separate point in this timeless space. Past, present, and future are all equally real, all existing simultaneously in an eternal four-dimensional tableau. We perceive temporal flow because our consciousness traces a path through these moments, like reading frames in a film strip. But the frames themselves don't change. They simply exist. If Barber is correct, then time itself, the arrow we desperately cling to, the flow we feel carrying us from moment to moment, might be nothing more than a perspectual illusion, a trick played by consciousness as it navigates through the static landscape of all possible realities. The second law of thermodynamics would still apply, but only because conscious observers tend to exist in parts of Platonia where entropy increases, since these are the regions where complex information processing systems like brains can exist. Alternatively, some cosmologists have turned to the multiverse hypothesis for answers. Perhaps our observable universe represents just one bubble in an infinite cosmic foam, where countless other universes exist with different physical laws, different initial conditions, and different entropy states. In most of these cosmic bubbles, entropy might begin at maximum values, with no temporal flow whatsoever, just static, high entropy equilibrium, extending throughout their entire histories. Our universe could be a statistical anomaly, an extraordinarily rare low-entropy pocket within this infinite multiverse. Just as we might occasionally see all the air molecules in a room randomly concentrate in one corner, an event so improbable it would happen perhaps once in longer than the age of the universe. Our low-entropy beginning might represent a similarly rare fluctuation in the multiverse's entropy distribution. The anthropic principle supports this interpretation. We find ourselves in a universe with low initial entropy, not because such universes are common, but because only such universes can give rise to complex structures like stars, planets, and life itself. Observers like us can only exist in the rare cosmic bubbles where entropy starts low and increases over time, creating the conditions necessary for complexity to emerge. Recent developments in cosmology have added new wrinkles to these ideas. Inflationary cosmology suggests that our observable universe underwent a period of exponential expansion in its first fraction of a second, stretching quantum fluctuations to cosmic scales. This inflation might provide a mechanism for establishing low-entropy initial conditions, but it also raises new questions about what caused inflation to begin and end. Some physicists have proposed that inflation itself might be eternal, continuously creating new pocket universes with different properties. In this eternal inflation scenario, our universe's low-entropy beginning becomes less mysterious. It's simply one of countless possible starting conditions realized somewhere in the infinite multiverse. These explanations, while mathematically sophisticated and internally consistent, often feel like whispers in darkness, like grains of sand slipping through our fingers as we try to grasp the ultimate nature of time. Each theory offers tantalizing glimpses into possible solutions, but none yet provides a complete, satisfying picture of why time has an arrow. What we do know is that entropy continues to grow throughout our observable universe. Stars burn their nuclear fuel, converting hydrogen into heavier elements and radiating energy into space. Galaxies collide and merge in spectacular displays of gravitational interaction. Black holes consume matter and slowly evaporate through Hawking radiation. All of these processes increase the universe's total entropy, driving us inexorably toward what physicists call heat death, a final state of maximum entropy where no more work can be performed. In this distant future, perhaps 1,000 years from now, the universe will have exhausted all possibilities for rearrangement. Stars will have faded to cold ember remnants, black holes will have evaporated into elementary particles, and the cosmos will settle into a silent, cold equilibrium where temperature and density are uniform throughout space. At that point, time will effectively stop. Not because time itself ceases to exist, but because there will be no physical basis for distinguishing between past and future. Without entropy gradients to provide temporal direction, yesterday and tomorrow become meaningless concepts, but that ultimate fate lies unimaginably far in the future. For now, we exist in the universe's golden age, when entropy gradients still drive magnificent complexity. Shattered glass remains broken, cream swirls irreversibly into coffee, and tomorrow waits tantalizingly beyond our reach. Time flows forward like a vast cosmic river, carrying us along as unwitting passengers on a journey from the improbable order of the past toward the statistical certainty of future chaos. The arrow of time remains one of our universe's deepest and most unsettling mysteries, a puzzle that touches on fundamental questions about the nature of reality, consciousness, and existence itself. Yet somewhere, hidden within the mathematics of entropy, the frozen landscapes of timeless moments, or the infinite possibilities of the multiverse, the answer patiently waits. Whether we'll find it through further theoretical development, experimental observation, or some entirely new approach remains to be seen. But the search itself reveals something profound about human nature, our irrepressible drive to understand not just how the universe works, but why it works the way it does, and what our place might be within its grand temporal tapestry. Matter and antimatter asymmetry represents one of the most profound puzzles in modern cosmology, a mystery so fundamental that it questions the very reason for our existence. According to the standard model of particle physics and our best understanding of the early universe, we shouldn't be here. Not in the way we observe ourselves, not with galaxies spiraling majestically through the void, not with stars burning steadily through nuclear fusion, not with planets orbiting in gravitational harmony, and certainly not with conscious beings capable of pondering these very questions. The mathematics of fundamental physics demands perfect symmetry. For every particle of ordinary matter, every proton building atomic nuclei, every neutron providing nuclear stability, every electron orbiting in quantum shells, there should exist a corresponding antimatter twin with identical mass but opposite charge. Protons should be perfectly matched by antiprotons, electrons by positrons, neutrons by antineutrons. This isn't merely theoretical speculation. Antimatter is real, and we can create it in particle accelerators today. When matter encounters antimatter, the result is immediate and total, mutual annihilation. The two particles disappear completely, their entire mass converted to pure energy, according to Einstein's famous equation E=mc2. A single gram of matter meeting a gram of antimatter would release energy equivalent to 43,000 tons of TNT, more than the atomic bomb dropped on Hiroshima. The explosion produces nothing but high-energy photons and perhaps some fleeting elementary particles. If the universe had strictly followed the laws of symmetry during its formation, every particle should have been created alongside its antimatter partner. As the early universe cooled and these particles encountered each other, they should have annihilated completely, leaving behind nothing but a cold, empty void filled with electromagnetic radiation, this silent afterglow of cosmic annihilation. There would be no hydrogen to fuel stars, no carbon to form complex molecules, no planets to harbour life. The universe would be nothing more than a dilute sea of photons expanding through empty space. But clearly this catastrophic scenario didn't occur. Something, some subtle asymmetry, some tiny imbalance, disrupted the perfect symmetry between matter and antimatter. Matter won, and we exist today as witnesses to this ancient victory. However, the margin of victory was incredibly slim. Current observations suggest that for every billion particle-antiparticle pairs that formed in the universe's first moments, there was just one extra particle of ordinary matter, a surplus of merely 1 part in a billion. This seems like an almost negligible difference, but from this minute imbalance emerged everything we can observe: the hundreds of billions of galaxies, each containing hundreds of billions of stars, the vast clouds of interstellar gas and dust, the rocky planets and gas giants, and ultimately the complex chemistry that gave rise to life itself. Every atom in your body, every molecule of DNA, every protein carrying out cellular functions, all of it exists because of this tiny primordial asymmetry. The question that has haunted physicists for decades is deceptively simple, yet profoundly challenging. Why? What happened in those first, crucial moments after the Big Bang that tilted the cosmic scales ever so slightly in favour of matter over antimatter? How could such an unimaginably small difference in the early universe lead to the rich, complex reality we observe today? To understand this mystery, we must journey back not just to the Big Bang itself, but to the chaotic, superheated moments that followed. In the first microseconds after cosmic birth, when the universe was smaller than a proton and hotter than the core of any star, reality existed in a state almost impossible to comprehend. The universe was a seething, turbulent ocean of pure energy, where particles and antiparticles flickered in and out of existence according to the strange rules of quantum mechanics. At these extreme temperatures and densities, the familiar categories of matter and energy became meaningless. Protons, neutrons, and electrons couldn't yet exist in stable form. The universe was too hot, too energetic for composite particles to hold together. Instead, space was filled with a plasma of fundamental particles, quarks and antiquarks, leptons and antileptons, photons and exotic gauge bosons, all existing in thermal equilibrium. This was the universe in its most symmetric state. For every type of particle, there existed an equal number of antiparticles. The laws of physics at these energies displayed beautiful mathematical symmetries that seemed to guarantee this perfect balance would be maintained forever. Yet somehow, as the universe expanded and cooled, this pristine symmetry was broken. The theoretical framework for understanding how this symmetry breaking might have occurred was laid out in 1967 by Andrei Sakharov, a brilliant Soviet physicist who would later become famous as a human rights activist and Nobel Peace Prize winner. Sakharov identified three necessary conditions that must be satisfied simultaneously for the universe to generate a matter-antimatter asymmetry. First, there must be physical processes that violate what physicists call baryon number conservation, meaning that reactions could occur that create more matter particles than antimatter particles, or vice versa. In a perfectly symmetric universe, the total number of matter particles minus antimatter particles would always remain constant at zero. Sakharov realized that some mechanism must exist to change this balance. Second, there must be violations of charge conjugation and parity symmetry, known collectively as CP symmetry. This is a fundamental principle stating that if you replace every particle with its antiparticle, charge conjugation, and flip the spatial coordinates as if viewing them in a mirror, parity, the physics should remain unchanged. If CP symmetry were perfect, matter and antimatter would behave identically, making it impossible to generate an asymmetry between them. Third, the universe must have been out of thermal equilibrium during the period when these asymmetry-generating processes were occurring. In thermal equilibrium, all possible reactions proceed at rates that exactly balance their reverse reactions, preventing any net change in particle populations. Only by departing from equilibrium could the universe remember the results of asymmetry-generating processes. Sakharov's conditions provided a theoretical roadmap, but finding evidence for the actual physical processes remained extraordinarily challenging. The breakthrough came in 1964, when American physicists James Cronin and Val Fitch conducted a seemingly routine experiment studying the decay of particles called neutral kaons at the Brookhaven National Laboratory. Kaons are unstable particles composed of a quark and an antiquark. They decay rapidly into lighter particles, and the mathematical laws governing these decays were thought to respect CP symmetry perfectly. However, Cronin and Fitch discovered something unexpected. Kaons and their antimatter counterparts, antikaons, decayed in slightly different ways. The difference was tiny, occurring in only about 2 out of every 1,000 decays, but it was real and repeatable. This discovery of CP violation sent shockwaves through the physics community. Here was direct experimental evidence that nature does indeed have a subtle preference for matter over antimatter, at least in certain rare processes. For their groundbreaking work, Cronin and Fitch were awarded the Nobel Prize in Physics in 1980. However, there was a problem. The CP violation observed in kaon decays was far too small to account for the antimatter asymmetry we observe in the universe today. If this were the only source of asymmetry, the tiny imbalance it could generate would be completely negligible compared to what's needed to explain our matter-dominated cosmos. It was like finding a barely visible crack in a massive dam and trying to claim it could explain the complete draining of a reservoir. Clearly, additional and much more powerful sources of CP violation had to exist in the early universe. This realization launched a decades-long search for the physical mechanisms responsible for generating the cosmic matter-antimatter asymmetry, a quest that continues today with experiments at the world's most advanced particle accelerators and neutrino detectors. One particularly promising avenue of research focuses on neutrinos, those ghostly particles that barely interact with ordinary matter. Neutrinos are produced copiously in nuclear reactions, including those occurring in the Sun's core. Every second, about 65 billion neutrinos from the Sun pass through every square centimetre of Earth's surface, but they're so weakly interacting that they travel through our planet as if it were completely transparent. Some theories propose that neutrinos might be Majorana particles, exotic entities that are their own antiparticles. If this is true, then in the early universe, heavy neutrino-like particles could have decayed in ways that violated CP symmetry much more dramatically than anything observed in kaons. This process, known as leptogenesis, could have created a primordial imbalance in the number of matter versus antimatter particles. The beauty of leptogenesis lies in its connection to phenomena we can potentially observe today. If neutrinos are indeed Majorana particles, then extremely rare nuclear decays called neutrinoless double beta decay should occasionally occur. Detecting such decays would provide indirect evidence for the same physics that might have generated the matter-antimatter asymmetry in the early universe. Experiments designed to search for neutrinoless double beta decay are among the most technically challenging ever attempted. Scientists must shield their detectors from cosmic rays by placing them deep underground, sometimes in mines more than a mile beneath the Earth's surface. They must also eliminate virtually all sources of radioactive contamination, as even tiny amounts of natural radioactivity could mimic the signal they're looking for. Despite decades of increasingly sensitive searches, neutrinoless double beta decay has never been definitively observed. The experiments continue to push the boundaries of detection technology, and each null result places tighter constraints on theories of neutrino masses and the physics of the early universe. Another possibility is that the matter-antimatter asymmetry was generated through processes involving particles and forces that we haven't yet discovered. Many theoretical extensions of the Standard Model predict the existence of new particles with masses far beyond what current accelerators can reach. These hypothetical particles might have played crucial roles in the early universe, participating in reactions that generated matter-antimatter asymmetries through mechanisms we can barely imagine. Some physicists have proposed that the asymmetry might be connected to the mysterious dark matter that makes up about 85% of the universe's matter content. Perhaps the same processes that generated the cosmic matter-antimatter asymmetry also produced the dark matter particles that we now detect through their gravitational effects on galaxies and galaxy clusters. There's also a more radical possibility that challenges our basic assumptions about the universe's structure. What if antimatter isn't actually missing at all? What if it exists in equal quantities to ordinary matter, but is somehow separated from us by vast cosmic distances? This idea leads to the concept of antimatter domains, hypothetical regions of space where antimatter has gravitationally condensed to form antimatter stars, antimatter planets, and even antimatter galaxies. If such domains exist, they would necessarily be separated from ordinary matter regions by enormous voids, because any contact zone between matter and antimatter would be marked by spectacular annihilation events. The gamma rays produced by large-scale matter-antimatter annihilation would be among the most energetic phenomena in the universe, easily detectable by our space-based telescopes. Astronomers have searched extensively for such signals, the telltale signatures of cosmic-scale annihilation, but have found nothing. The absence of these gamma-ray signals strongly suggests that if antimatter domains exist at all, they must be incredibly rare and located far beyond our observable horizon. Recent advances in our understanding of particle physics have opened up new avenues for investigating the matter-antimatter mystery. The discovery of neutrino oscillations, the phenomenon where neutrinos change from one type to another as they travel through space, has revealed that neutrinos have mass, contrary to the predictions of the original Standard Model. This finding suggests that our understanding of neutrino physics is still incomplete, and that more surprises may be waiting. Experiments at the Large Hadron Collider, LHC, in Switzerland, the world's most powerful particle accelerator, continue to probe the fundamental nature of CP violation. By colliding protons at energies 7 times higher than any previous accelerator, the LHC can create conditions similar to those that existed in the universe just moments after the Big Bang. Physicists hope that these experiments might reveal new particles or forces responsible for generating the cosmic matter-antimatter asymmetry. The LHCb experiment, one of several detector systems at the LHC, is specifically designed to study particles containing bottom quarks, cousins of the strange quarks found in the kaons that first revealed CP violation. These experiments have already discovered several new examples of CP violation, each providing additional clues about the underlying physics. Meanwhile, theoretical physicists continue to develop increasingly sophisticated models of the early universe, incorporating insights from string theory, extra dimensions, and quantum gravity. Some of these models predict that the matter-antimatter asymmetry was established during cosmic inflation, a period of exponential expansion that occurred in the universe's first tiny fraction of a second. Others suggest that the asymmetry emerged later, during phase transitions as the universe cooled and fundamental forces took on their current forms. The implications of solving the matter-antimatter mystery extend far beyond academic curiosity. Understanding why the universe contains matter could provide crucial insights into the nature of time, the origin of physical laws, and the ultimate fate of the cosmos. It might also lead to practical applications in energy production, space propulsion, and medical imaging, technologies that harness the tremendous energy released by matter-antimatter annihilation. As we continue to probe this ancient cosmic mystery, we're reminded of a profound truth. Our entire existence, every star that lights the night sky, every planet that orbits those stars, every molecule of water and oxygen that sustains life, owes its presence to an incredibly subtle imperfection in the universe's fundamental symmetries. We exist because the cosmos, in its earliest moments, broke its own rules just enough to allow complexity, structure, and ultimately consciousness to emerge from what should have been perfect sterile symmetry. The universe's preference for matter over antimatter represents one of the most consequential flaws in nature, a tiny deviation from mathematical perfection that made everything else possible. Whether this asymmetry arose from known physics operating under extreme conditions, or from exotic new phenomena beyond our current understanding, remains one of the greatest open questions in science. Every time physicists fire up a particle accelerator, every time they lower a detector into an underground laboratory, every time they point a telescope toward a distant galaxy, they're participating in humanity's ongoing effort to understand this primordial imbalance. The answer, when it finally comes, will not just explain why matter exists, it will illuminate the deepest principles governing reality itself and our place within the cosmic story that began with the Big Bang and continues to unfold around us today. Quantum tunneling stands as one of the most counterintuitive and fascinating phenomena in all of physics, challenging our most basic assumptions about how reality operates at its fundamental level. On the surface, our universe appears to follow a dependable set of rules, what we might call reality's rulebook. These laws seem steadfast and reliable. Dropped objects fall downward under gravity's influence. Heat always flows from hot regions to cold ones. Solid walls stop moving objects in their tracks. The macroscopic world around us behaves predictably according to classical physics, the mathematical framework developed by Newton and refined by countless scientists over centuries. But beneath this seemingly stable surface, deep within the quantum realm where atoms and subatomic particles reign supreme, reality begins to misbehave in the most extraordinary ways. At these microscopic scales, particles don't obey the same intuitive rules that govern our everyday experience. They flicker in and out of existence, exist in multiple states simultaneously, become entangled across vast distances, and perhaps most remarkably of all, they can accomplish what appears to be an utterly impossible feat, passing through solid barriers as if those barriers weren't there at all. This phenomenon is quantum tunneling, and it represents one of the strangest and most consequential aspects of quantum mechanics. To understand just how bizarre this process is, imagine yourself standing before an enormous mountain that stretches impossibly high into the clouds. In our classical world, you would have limited options. You could spend years climbing over the summit. You could attempt to dig a tunnel through the rock, or you could simply walk around the mountain's base. But under no circumstances would you expect to simply walk straight through the mountain as if it were made of thin air, emerging unharmed on the other side. Yet this is essentially what quantum particles routinely do. Electrons, protons, neutrons, and even entire atoms have been observed performing this seemingly impossible escape act, passing through energy barriers that should, by all classical reasoning, be completely impenetrable. They don't go over the barriers, they don't go around them, they somehow pass directly through them, appearing on the other side with no clear explanation of how they made the journey. To understand how quantum tunneling works, we must first fundamentally reshape our understanding of how particles behave at the quantum level. In our everyday macroscopic experience, objects are distinct, well-defined entities with specific locations and properties. A marble sitting on a table is unambiguously either in one place or another. There's no ambiguity about its position or state of motion. But in the quantum realm, this comfortable certainty evaporates. Particles don't possess definite positions or velocities in the way we typically imagine. Instead, they exist as what physicists call probability waves or wave functions, mathematical descriptions that capture all the possible states a particle might be found in when measured. These aren't mere mathematical abstractions. They represent a fundamental aspect of reality at quantum scales. Picture throwing a stone into the center of a perfectly calm pond. The impact creates ripples that spread outward in all directions, carrying energy away from the point of disturbance. In a similar way, a quantum particle's wave function spreads across space, but instead of carrying energy, it carries probability, the likelihood of finding the particle at different locations if someone attempts to measure its position. This wave-like nature of matter was first proposed by French physicist Louis de Broglie in 1924 and later confirmed through numerous experiments. The famous double-slit experiment demonstrates this particle-wave duality most dramatically. When individual electrons are fired through two parallel slits toward a detector screen, they create an interference pattern, alternating bands of high and low intensity, exactly as waves would do. Each electron somehow passes through both slits simultaneously, interfering with itself to create the observed pattern. Now here's where quantum tunneling enters the picture. Imagine placing a barrier, a potential energy wall, in the path of a classical wave in water. The wave might partially reflect off the barrier, but some portion of it would likely leak through to the other side, especially if the barrier isn't perfectly opaque. Quantum mechanically, something similar happens with particle wave functions. When a quantum particle encounters an energy barrier that it doesn't have enough energy to classically surmount, its wave function doesn't simply stop at the barrier's edge. Instead, the wave function extends into the forbidden region beyond the barrier, though with rapidly diminishing amplitude. If the barrier isn't too thick, some non-zero portion of the wave function emerges on the far side. This means there's a calculable probability, often tiny but never exactly zero, that the particle will be found on the other side of the barrier, having somehow tunneled through it. The mathematics of this process were worked out in the early days of quantum mechanics by physicists like Friedrich Hund and others. The probability of successful tunneling depends on several factors: the particle's mass and energy, the height of the energy barrier, and crucially, the barrier's thickness. For very thick barriers, the tunneling probability becomes vanishingly small. For thin barriers, it can be surprisingly large. This isn't merely abstract theory with no practical consequences. Quantum tunneling is responsible for some of the most important processes in the universe, starting with the nuclear fusion reactions that power every star in the night sky. Inside the core of our Sun, hydrogen nuclei, protons, must overcome the powerful electromagnetic repulsion between their positive charges to get close enough for the strong nuclear force to bind them together in fusion reactions. Classically, the protons in the Sun's core don't have nearly enough thermal energy to surmount this electromagnetic barrier. The temperature would need to be roughly 10 times higher than the Sun's actual core temperature for classical fusion to occur efficiently. Yet fusion happens constantly, releasing the energy that has sustained life on Earth for billions of years. The secret is quantum tunneling. The protons tunnel through the electromagnetic energy barrier, allowing fusion to occur at the Sun's actual temperature. This process, first understood in detail by physicists George Gamow and others in the late 1920s, revolutionized our understanding of stellar physics and cosmology. Without quantum tunneling, stars like our Sun couldn't exist in their current form, and the universe would be a much colder, darker place incapable of supporting the chemistry necessary for life. On Earth, quantum tunneling forms the operational foundation of numerous modern technologies that have transformed human civilization. One of the most elegant applications is the Scanning Tunneling Microscope, STM, invented by Gerd Binnig and Heinrich Rohrer at IBM in the early 1980s. This remarkable instrument exploits the exponential sensitivity of quantum tunneling to distance, allowing scientists to observe and manipulate individual atoms on surfaces. The STM works by bringing an atomically sharp metal tip extremely close to a conducting surface, so close that the electron wave functions of the tip atoms overlap slightly with those of the surface atoms. When a small voltage is applied between the tip and surface, electrons can tunnel across the tiny gap, creating a measurable current. As the tip scans across the surface, variations in the tunneling current reveal the positions of individual atoms with unprecedented precision. This technology has opened up entirely new fields of research and engineering at the atomic scale. Scientists can now not only see individual atoms, but also move them around to create artificial structures, study chemical reactions in real time, and probe the electronic properties of materials with atomic-level resolution. The STM and its variants have been instrumental in developing nanotechnology, quantum devices, and our understanding of surface physics. Flash memory, the technology that stores data in smartphones, tablets, and USB drives, also relies fundamentally on quantum tunneling. In these devices, information is stored by trapping electrons in tiny semiconductor structures called floating gates. To write data, electrons are forced to tunnel through thin insulating barriers to reach these gates, where they remain trapped for years or even decades. To erase data, the electrons tunnel back out through the same barriers. The ability to precisely control quantum tunneling in these devices has made possible the digital revolution that connects billions of people worldwide. Every photo you save, every message you send, every app you download depends on electrons tunneling through barriers just a few atoms thick. Quantum tunneling also plays crucial roles in more exotic technologies. Josephson junctions, created when two superconducting materials are separated by a thin insulating barrier, allow Cooper pairs of electrons to tunnel across the gap without resistance. These devices form the basis of superconducting quantum interference devices, SQUIDs, which are among the most sensitive magnetic field detectors ever created, capable of measuring magnetic fields billions of times weaker than Earth's magnetic field. Despite its technological importance and mathematical precision, quantum tunneling continues to challenge our philosophical understanding of reality. How can a particle pass through a region where it's forbidden to exist? What exactly happens during the tunneling process? These questions probe the very foundations of quantum mechanics and our interpretation of what it means for something to exist. Recent experimental advances have allowed physicists to probe the tunneling process with unprecedented detail. Using attosecond laser pulses, flashes of light lasting only billionths of a second, scientists can now observe what happens during tunneling events in real time. These experiments have revealed that tunneling is even stranger than previously thought. Some studies suggest that particles don't simply pop instantaneously from one side of a barrier to the other. Instead, they seem to spend a measurable amount of time interacting with the barrier itself, as if they're somehow exploring the forbidden region before deciding whether to tunnel through or reflect back. Other experiments hint that the tunneling process might be instantaneous, or even that particles somehow arrive on the far side of barriers before they've had time to classically traverse the distance. These timing measurements have reopened fundamental questions about the nature of quantum mechanics that physicists thought were settled decades ago. They're forcing us to reconsider what we mean by concepts like duration and trajectory in the quantum world, and whether particles follow definite paths at all during tunneling events. The implications extend far beyond laboratory curiosities. Some theoretical physicists have proposed that quantum tunneling might provide clues about the structure of space-time itself at the smallest scales. If space and time are quantized, made up of discrete units rather than forming a smooth continuum, then what we interpret as tunneling through energy barriers might actually represent transitions between different quantum states of space-time geometry. Other researchers have speculated about connections between quantum tunneling and cosmology. Some models of cosmic inflation, the period of exponential expansion thought to have occurred in the universe's first fraction of a second, invoke quantum tunneling between different vacuum states. In these scenarios, our entire observable universe might represent the outcome of a cosmic scale tunneling event that occurred 13.8 billion years ago. There are also tantalizing hints that quantum tunneling might be related to the mystery of consciousness itself. Some theories propose that quantum effects in the brain, including tunneling processes in microtubules or other cellular structures, could play a role in generating conscious experience. While these ideas remain highly speculative and controversial, they illustrate the profound implications that quantum phenomena might have for our understanding of mind and reality. As physicists continue to push the boundaries of what's possible with quantum tunneling, they're exploring increasingly exotic scenarios. In laboratory settings, scientists have successfully demonstrated tunneling of not just individual particles, but entire atoms and even small molecules through barriers. Some researchers are working to tunnel larger and larger objects, testing the limits of quantum behavior and probing the boundary between the quantum and classical worlds. The question of whether macroscopic objects, viruses, living cells, or even human beings could theoretically tunnel through barriers remains one of the most fascinating thought experiments in physics. The mathematics of quantum mechanics doesn't explicitly forbid such possibilities, but the probabilities involved become astronomically small for objects containing many particles. For a human being to quantum tunnel through a solid wall, every single particle in the body, roughly 7 × 10^27 atoms, would need to tunnel through simultaneously in a coordinated manner. The probability of this occurring is so unimaginably tiny that it approaches zero for all practical purposes. You would have better odds of randomly arranging all the letters in all the books ever written into perfect alphabetical order by shaking them in a giant container. Yet the fact that such events aren't strictly impossible according to quantum mechanics highlights one of the most profound aspects of our universe. At its deepest level, reality operates according to probabilities rather than certainties. The apparent solidity and predictability of the macroscopic world emerges from the statistical behavior of countless quantum particles, each following probabilistic rules that allow for seemingly impossible outcomes. This probabilistic foundation of reality has philosophical implications that continue to challenge our worldview, centuries after quantum mechanics was first developed. It suggests that the universe is fundamentally uncertain at its base level, with definite outcomes only emerging through the collective behavior of vast numbers of quantum systems. As we continue to explore the frontiers of quantum tunneling, we're not just advancing technology or satisfying scientific curiosity, we're probing the deepest questions about the nature of existence itself. Every tunneling experiment, Every new application, every theoretical insight brings us closer to understanding the strange, beautiful, and utterly unexpected ways that reality operates at its most fundamental level. The next time you take a digital photograph, send a text message, or simply gaze up at the stars shining in the night sky, remember that you're witnessing the consequences of quantum tunneling in action. Somewhere in your device's memory, electrons are tunneling through barriers to store information. Above you, in the cores of distant stars, protons are tunneling through electromagnetic barriers to fuse and create the light that reaches your eyes across vast cosmic distances, and perhaps most remarkably of all, these same quantum mechanical processes that seem so alien to our everyday experience are operating constantly within your own body. In every cell, electrons tunnel between molecules during photosynthesis in plants you eat, enzyme reactions that break down food for energy, and countless other biochemical processes that sustain life itself. Quantum tunneling reminds us that the universe is far stranger, more subtle, and more beautiful than our classical intuitions would suggest. It reveals a reality where the impossible becomes merely improbable, where particles can exist in multiple states simultaneously, and where the very act of observation can change the outcome of quantum events. As we stand on the threshold of new quantum technologies, quantum computers, quantum communication networks, quantum sensors, we're just beginning to harness the full potential of these strange quantum phenomena. The future may hold applications of quantum tunneling that we can barely imagine today, from revolutionary medical devices to spacecraft propulsion systems to methods of energy production that tap into the quantum vacuum itself. But perhaps the greatest gift that quantum tunneling offers us is perspective, a reminder that reality at its deepest level operates according to principles that transcend our everyday experience and challenge us to expand our understanding of what's possible in this extraordinary universe we call home. The oh my god particle represents one of the most extraordinary and puzzling discoveries in modern astrophysics, a discovery that challenges our understanding of the universe's most extreme physical processes and hints at phenomena that stretch the very limits of known physics. To truly appreciate the magnitude of this mystery, we must first grasp the almost incomprehensible scale of energy involved when a single subatomic particle, smaller than an atom, invisible to the naked eye, weighing less than a billionth of a gram, carries enough kinetic energy to knock over a bowling pin. This isn't merely an academic thought experiment or science fiction speculation. These particles are real. They exist in our universe right now, and they're called ultra-high energy cosmic rays. They represent the fastest moving, most energetic individual particles ever detected, and they arrive at Earth as mysterious messengers from the most violent and extreme corners of the cosmos. Cosmic rays themselves have been known to science for over a century, first discovered by Austrian physicist Victor Hess in 1912, when he noticed that radiation levels increased with altitude during balloon flights, clear evidence that high-energy particles were raining down on Earth from outer space. But ultra-high-energy cosmic rays occupy a realm far beyond ordinary cosmic radiation, carrying energies that dwarf anything we can produce in our most advanced particle accelerators by factors of millions or even billions. The story of the oh my god particle begins on the night of October 15, 1991, at the Fly's Eye Detector facility in Utah's remote desert. This observatory, consisting of mirrors and photomultiplier tubes arranged to detect flashes of fluorescent light in the atmosphere, was designed to observe the aftermath of cosmic ray collisions with air molecules high above Earth's surface. That evening, the automated systems recorded something so extraordinary that researchers initially suspected instrumental error or data corruption. A single cosmic ray had slammed into Earth's atmosphere with an energy of approximately 3.2 x 10⁻20 electron volts, equivalent to about 51 joules of kinetic energy. To put this in perspective, imagine a baseball traveling at about 100 kilometers per hour. That baseball and this subatomic particle carried roughly the same amount of kinetic energy, despite the particle being roughly 1017 times smaller in mass than the baseball. The researchers dubbed it the "Oh my God" particle, and the name stuck not just for its memorable quality, but because it captured the genuine astonishment felt by physicists around the world. Here was a single proton, or possibly a heavier atomic nucleus, that had somehow been accelerated to an energy level over 40 million times higher than anything achievable at CERN's Large Hadron Collider, the most powerful particle accelerator ever built by humans. If we were to scale this proton up to the size of a tennis ball while preserving its energy to mass ratio, it would be travelling at nearly the speed of light with the kinetic energy of a rifle bullet. The implications were staggering and deeply puzzling. How could a single particle achieve such enormous energy? And what cosmic accelerator could possibly be responsible for creating it? According to our best understanding of particle physics and astrophysics, particles of such extreme energy shouldn't even be able to reach Earth from distant sources. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently predicted a theoretical energy cutoff for cosmic ray protons arriving from distant galaxies. This became known as the GZK cutoff, named after the three scientists. The GZK cutoff arises from interactions between ultra-high energy cosmic rays and the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that permeates all of space. For protons travelling at extreme energies across cosmic distances, this background radiation doesn't appear as gentle microwaves but as high-energy gamma rays due to relativistic effects. These gamma rays can trigger photopion production, where the cosmic ray proton interacts with the background photon to produce pions, dramatically reducing the proton's energy. The upshot is that cosmic ray protons above a certain energy threshold, about 6 × 1019 electron volts, should lose energy so rapidly through these interactions that they can't maintain their extreme energies over distances greater than about 150–300 million light-years. This distance might sound enormous, but in cosmological terms it's relatively local. It encompasses our nearby galactic neighbourhood, but excludes the vast majority of the observable universe. Yet the "Oh my God" particle and several other ultra-high energy events detected since then appear to violate this fundamental prediction. If these particles originated from nearby sources within the GZK sphere, we should be able to identify their origins by tracing their paths backward through space. But cosmic magnetic fields deflect charged particles as they travel, scrambling their trajectories and erasing clear directional information about their sources. This leads us into a cosmic detective story with few clear clues and multiple possible suspects. What natural phenomena could possibly accelerate particles to such extreme energies? The prime suspects are some of the most violent and energetic events in the known universe. Supermassive black holes lurking at the centers of galaxies represent one leading candidate. These gravitational monsters, containing millions to billions of times the mass of our Sun, can create some of the most extreme physical conditions in the universe. When matter falls toward a supermassive black hole, it doesn't simply disappear. It first forms a swirling accretion disk where material is heated to millions of degrees and accelerated to significant fractions of light speed. In many cases, supermassive black holes also launch enormous jets of material perpendicular to their accretion disks. These relativistic jets, powered by the rotation of the black hole and magnetic field interactions, can extend for millions of light years into space and shine brighter than entire galaxies. Within these jets, particles experience electromagnetic fields of unimaginable strength, potentially providing the acceleration needed to reach ultra-high energies, active galactic nuclei. Galaxies with particularly energetic supermassive black holes at their centers have indeed been proposed as sources of ultra-high energy cosmic rays. Observations show that some of these objects can accelerate particles to enormous energies, though whether they can reach the extreme energies of the oh my god particle remains an open question. Another class of suspects includes gamma-ray bursts, the most luminous electromagnetic events known in the universe. These cosmic explosions, likely triggered by the collapse of massive stars into black holes or the collision of neutron stars, can briefly outshine entire galaxies and release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. The extreme conditions during gamma-ray bursts, involving magnetic fields trillions of times stronger than Earth's and shock waves travelling at near light speed, could potentially create the natural particle accelerators needed to produce ultra-high energy cosmic rays. Some theoretical models suggest that the afterglow phases of gamma-ray bursts, which can persist for weeks or months after the initial explosion, might be particularly effective at accelerating particles to extreme energies. However, there's a significant problem with both the supermassive black hole and gamma-ray burst hypotheses. When astronomers have attempted to trace ultra-high energy cosmic rays back to their apparent sources, they often don't find obvious candidates in the expected directions. The particles seem to arrive from random directions in the sky, as if they're cosmic orphans with no clear parents. This directional puzzle has led some physicists to propose more exotic explanations that push the boundaries of known physics. Perhaps these particles aren't ordinary protons or atomic nuclei at all, but something far stranger, exotic matter that interacts differently with the cosmic microwave background radiation and cosmic magnetic fields. One intriguing possibility involves hypothetical particles called strangelets, theoretical forms of quark matter that could be more stable than ordinary atomic nuclei. If strangelets exist and can be accelerated to ultra-high energies, they might behave differently than ordinary matter during their journey through space, potentially explaining some of the observed anomalies. Even more speculative theories propose that ultra-high energy cosmic rays might be leaking into our universe from parallel dimensions or alternate realities. In some models of string theory and extra-dimensional physics, our familiar three-dimensional space might be just one slice of a higher dimensional reality called the bulk. Particles might occasionally cross between different three-dimensional branes within this bulk, arriving in our universe with energies that seem impossible by our local physical laws. Another mind-bending possibility is that these cosmic rays reveal fundamental flaws in our understanding of space-time itself. At the most extreme energies, approaching the scale where quantum gravitational effects might become important, the familiar concepts of space, time, and matter might break down entirely. Perhaps ultra-high energy cosmic rays are probing physics beyond the standard model, offering glimpses of new particles, forces, or dimensions that only manifest under the most extreme conditions. The experimental investigation of ultra-high energy cosmic rays requires some of the most sophisticated and ambitious scientific instruments ever constructed. Because these particles are so rare, arriving at a rate of roughly 1 per square kilometre per century, detecting them requires enormous detector arrays covering hundreds or thousands of square kilometres. The Pierre Auger Observatory in Argentina represents the current state of the art in cosmic ray detection. Covering an area of 3,000 square kilometres, larger than the state of Rhode Island, this facility combines two complementary detection techniques to catch and analyse ultra-high energy cosmic ray events. The first technique involves an array of 1,060 water Cherenkov detectors distributed across the Pampas Argentinas. Each detector consists of a tank filled with ultra-pure water and monitored by sensitive photomultiplier tubes. When a cosmic ray strikes Earth's atmosphere, it creates a cascade of secondary particles that shower down across a wide area. These secondary particles travel faster than light can move through water, creating flashes of blue Cherenkov light that the detectors can measure. The second technique uses fluorescence telescopes, arrays of mirrors and cameras that look upward into the dark desert sky. When cosmic ray particles collide with nitrogen molecules in the atmosphere, they cause the nitrogen to fluoresce, emitting ultraviolet light. By tracking this faint glow as the cosmic ray shower develops through the atmosphere, scientists can reconstruct the energy and direction of the original particle with remarkable precision. Similar facilities exist around the world, including the Telescope Array project in Utah and planned next-generation observatories that will push sensitivity even further. Each detection provides crucial data about the energy spectrum, arrival directions, and composition of ultra-high energy cosmic rays, slowly building a picture of these mysterious particles. What this data has revealed is a universe far more complex and violent than we might have imagined. Ultra-high energy cosmic rays arrive from all directions, with no obvious correlation to known astronomical objects. Their energy spectrum shows interesting features, including a possible ankle at moderate energies and a potential cutoff at the highest energies, that might provide clues about their acceleration mechanisms and propagation through space. Recent years have brought tantalizing hints about the composition of ultra-high energy cosmic rays. While the oh my god particle was likely a proton, other ultra-high energy events seem to involve heavier atomic nuclei, perhaps iron, silicon, or other elements forged in the nuclear furnaces of massive stars. This compositional information provides important clues about both the sources of these particles and the processes that accelerate them. The mystery has also driven advances in theoretical physics and astrophysics. Scientists have developed increasingly sophisticated computer simulations that model cosmic ray acceleration in various astrophysical environments, from the magnetospheres of rotating black holes to the shock fronts of supernova remnants. These simulations help identify which scenarios can realistically produce particles of the required energies and predict their observable signatures. Meanwhile, the search continues for new physics beyond the standard model that might explain ultra-high energy cosmic ray anomalies. Some theories propose that these particles might be decay products of extremely massive, long-lived particles created in the early universe, relics from cosmic inflation or phase transitions that occurred moments after the Big Bang. Others suggest connections to dark matter, the mysterious substance that makes up most of the universe's mass, but interacts only gravitationally with ordinary matter. The implications of solving the ultra-high energy cosmic ray mystery extend far beyond academic physics. Understanding the sources and acceleration mechanisms of these particles could provide insights into the most extreme astrophysical environments in the universe, help us map the large-scale structure of cosmic magnetic fields and potentially reveal new fundamental physics. From a practical standpoint, ultra-high energy cosmic rays also pose challenges for future space exploration and technology. A single ultra-high energy particle striking a spacecraft or satellite could potentially cause significant damage to electronic systems, though the extremely low flux of such particles makes this a manageable risk for current missions. As we continue to build more sensitive detectors and accumulate more data, we're slowly piecing together the cosmic puzzle that began with that remarkable detection on October 15th, 1991. Each new ultra-high energy event adds another piece to the picture, bringing us closer to understanding not just where these particles come from, but what they tell us about the fundamental nature of our universe. The story remains unfinished, full of tantalizing clues and persistent mysteries. The origins of ultra-high energy cosmic rays continue to elude us. Their impossible energies still challenge our theoretical frameworks, and every new detection reminds us how much we still don't understand about the universe's most extreme phenomena. Perhaps the next cosmic ray detection will provide the breakthrough insight that solves this decades-old puzzle. Or perhaps these mysterious messengers will continue to challenge our understanding, pushing us toward new physics and new ways of thinking about the cosmos. Either way, somewhere out there in the vast darkness between galaxies, another ultra-high energy particle is already on its way toward Earth, carrying with it secrets from the universe's most violent and exotic corners, secrets we've only just begun to decode. White holes occupy cosmic theatre as enigmatic characters. Black holes are bottomless pits where gravity reigns supreme and light cannot escape. Cosmic one-way doors where time distorts and matter meets unknowable fates. But what if another door type existed? Not for entering, but exiting. Mirror images of black holes, theoretical objects where nothing enters, only exits. These hypothetical objects are white holes. At first glance, white holes sound more science-fictional than scientific. They're mathematical predictions, black hole cousins emerging from identical Einstein general relativity equations. While black holes are well observed across universe, white holes remain elusive, perhaps non-existent, yet among theoretical physics' most tantalizing mysteries. Understanding white holes requires revisiting their counterparts. In 1915, Albert Einstein published General Relativity, mathematical masterpiece redefining gravity, space, and time understanding. Soon after, physicist Carl Schwarzschild solved Einstein's equations for particularly extreme scenarios. What happens when massive objects collapse under their own weight, compressing all mass into infinitely small points, singularities? Results were Schwarzschild metrics, first mathematical black hole descriptions. But buried within solutions was something strange, equally valid yet almost alien second solutions. It described objects with reversed time-like properties. Instead of pulling everything inward, these objects pushed everything outward. Instead of cosmic traps, they were cosmic fountains. Schwarzschild solutions had unintentionally predicted white holes. While black holes arise naturally from collapsing stars with abundant observational evidence, white holes have fundamental problems. They seem impossible to create. Black holes are born from collapse when stars burn through fuel, and gravitational forces crush them into infinitesimal singularities. But for white holes to exist, they'd have to emerge already formed, fully intact, with nothing ever having entered. Unlike black holes devouring everything in their paths, white holes would be eternally sealed from outside universe. It's like witnessing upward flowing waterfalls. In real universe, white holes seem forbidden by thermodynamics' second law. This law dictates that entropy, disorder measures, must always increase. White holes constantly spitting out matter and energy in orderly manners would represent universes where entropy decreases. That simply doesn't happen. Yet mathematics stubbornly insists white holes are possible. Gamma-ray bursts, short, intense high-energy radiation flashes, are among universe's most energetic events. They're so brief, powerful, and mysterious that scientists still don't fully understand their causes. Some researchers speculate, could gamma-ray bursts be white holes' final size? Could these sudden chaotic emissions represent final matter escapes from impossibly ancient white holes, ones collapsing or vanishing into non-existence? It's speculative, very speculative, but connections aren't entirely absurd. After all, if white holes exist, their signatures would be explosive, unpredictable, unlike anything seen before. Here's where things get stranger. What if black holes and white holes aren't separate entities but two sides of identical coins? Bridges? Wormholes connecting black hole singularities to white hole outflows in other universe regions, or entirely different universes? This idea comes from Einstein-Rosen bridges, theoretical space-time shortcuts predicted by relativity. In this scenario, every black hole would have white hole twins connected through wormholes. But there's a catch. These connections are inherently unstable. Slightest disturbances, say single stray photons, would cause wormhole collapses instantly, sealing off potential passages. Yet images remain haunting. Cosmic bridges where matter swallowed by black holes emerges somewhere, sometime from white holes. There's another equally bizarre idea. Black holes aren't eternal. They evaporate over time thanks to Hawking radiation. Slow, ghostly processes where energy leaks from black hole event horizons. As black holes shrink closer to nothingness, could they eventually reverse? Could dying black holes' final moments trigger white hole births, ejecting trapped contents back into universe in final chaotic energy bursts? It's an idea blending black holes, white holes, and quantum physics into breathtaking possibilities. At its core, white hole problems might not be relativity problems at all, but quantum gravity problems. Elusive theories uniting Einstein's grand cosmic scales with quantum mechanics' microscopic unpredictability. Some physicists speculate white holes might exist in quantum realms on unimaginably small scales, flickering in and out of existence tied to space-time's strange foam-like textures. They could be early universe remnants, tiny Big Bang echoes scattered throughout reality. But without quantum gravity theories, these ideas remain shadows on ignorance walls. After a century of speculation, white holes remain trapped in theoretical realms. They're mathematical echoes, beautiful but intangible, carved into universe equations but absent from telescopes. Perhaps they're impossible, prohibited by fundamental nature laws. Perhaps they're out there, hidden beyond cosmic horizons, fleeting and rare, waiting for discovery. Even if white holes never exist in our universe, their mathematics still teach profound lessons. Universe isn't just strange, it's stranger than imaginable. Somewhere in relativity equations, in gamma-ray burst whispers, or in evaporating black hole dying breaths, answers might wait. For now, white hole mysteries remain open doors, ones we cannot yet step through. Dark matter and dark energy represent cosmic shadows. In grand cosmic expanses amidst glittering star and galaxy tapestries exist unseen forces, shadowy presences dominating universe. They don't shine, reflect light, or interact with familiar worlds, yet without them, galaxies would fly apart, stars scatter into voids, and universe as we know it would collapse into chaos. This invisible force is dark matter. As if that weren't strange enough, something even more elusive lurks in space vastness. Mysterious energy pushing galaxies apart, stretching reality's fabric. We call it dark energy. Together, dark matter and dark energy comprise over 95% of universe. Everything visible, stars, planets, gas clouds, every atom and photon, accounts for less than 5%. The rest is darkness, not comforting night shadows but inscrutable, all-encompassing mystery woven into existence's structure. Dark matter's story begins nearly a century ago with astronomer Fritz Zwicky. In 1930s, Zwicky studied Coma Cluster, massive galaxy collections bound by gravity. Using Newton's motion laws, he calculated how fast these galaxies should move, based on clusters' visible mass, stars, gas, everything observable. Something didn't add up. Galaxies moved far too fast. By all accounts, they should have flown apart, scattering into cold space voids. Yet they stayed together, as if bound by unseen gravitational hands. Zwicky proposed something he called dunkel Materie, dark matter, invisible substances exerting gravitational pull, holding galaxies in place. Initially, few took him seriously. Decades later, astronomer Vera Rubin uncovered striking supporting evidence. Studying spiral galaxy rotation curves, Rubin noticed something bizarre. According to Newtonian physics, stars on galaxy outskirts should orbit more slowly than those near centers, much like solar system planets. But they didn't. Edge stars moved just as fast as closer ones, defying all expectations. The only explanation, unseen mass, dark matter halos enveloping galaxies, gravitational influence stretching far beyond visible stars. But what is dark matter? Despite profound universe influence, we still don't know. It doesn't emit light, absorb it, or collide with normal matter. Scientists believe it might be exotic particles, WIMPs, weakly interacting massive particles, or axions, hypothetical entities interacting only through gravity and weak nuclear forces. Experiments deep underground and in massive particle colliders search for these elusive particles, but so far dark matter remains machine ghosts. The mystery deepens because if dark matter is hidden, scaffolding holding galaxies together, dark energy is invisible hands pulling them apart. In late 1990s, two teams studying distant-type Ia supernovas made startling discoveries. They expected to find universe expansion slowing over time as gravity pulled galaxies back together. Instead, they found opposites. Universe isn't just expanding, it's accelerating. Something counteracts gravity on larger scales, driving galaxies apart at ever-increasing speeds. This repulsive force is dark energy, accounting for nearly 70% of universe's total energy density. Its discovery shattered cosmology understanding, raising questions still haunting physicists. What is dark energy? One idea ties it to vacuum energy, empty space properties. Quantum mechanics tells us even perfect vacuums aren't truly empty. They're frothing seas of virtual particles constantly appearing and vanishing. This energy, though minuscule, might accumulate across space vastness, creating cosmic pushes driving universe apart. Another theory links dark energy to Einstein's cosmological constant, terms he once introduced and later dismissed as mathematical fixes in general relativity equations. But with accelerating universe discoveries, This constant suddenly became one of physics' most important numbers. Yet when physicists tried calculating its value using quantum theory, they arrived at numbers 120 orders of magnitude too large. One of science's greatest mismatches, a discrepancy so vast it's dubbed vacuum catastrophe. Some physicists suggest dark energy isn't constant at all, but dynamic, evolving fields called quintessence. Unlike fixed cosmological constants, quintessence could change over time, subtly influencing cosmic fates. For now, these are just theories. Darkness whispers. Together, dark matter and dark energy paint pictures of universes both majestic and profoundly alien. They remind us how much we still don't understand. Cosmos are far stranger than ancestors could ever imagine. Yet despite mysteries, we can measure their effects. We see dark matter's gravitational pull in galaxy clustering ways. We observe dark energy-driven cosmic expansion in distant light redshifts. These invisible forces shape universe, sculpt galaxies, dictate cosmic fates, and set stages for everything we see. But stories aren't over. Dark matter particle searches continue in underground laboratories, where detectors sit patiently, waiting for single elusive particles to leave marks. Astronomers peer deeper into space, searching for faintest dark energy clues in distant star and galaxy light. In the end, dark matter and dark energy remind us of humbling truths. Universe isn't what it seems. Most exists beyond sense veils. In darkness, realms we're only beginning to explore. Perhaps most profound questions aren't what dark matter and dark energy are, but why they exist at all. Why does universe have this delicate balance? Cosmic tugs of war between invisible forces holding it together and those tearing it apart. Maybe answers await us in space depths, in gravitational wave hums, or in particle detector quiet stillness buried deep underground. Maybe universe will guard secrets a little longer. For now, we're left with cosmos dominated by shadows, by forces we cannot see but cannot ignore. In those shadows, hidden behind mystery veils, lies keys to understanding not just universe, but our places within it. In vast space expanses amidst silent galaxy dances and infinite void stretches, universe holds its breath. Somewhere in starlight flickers and distant quasar hums, answers await, waiting for us to notice. Darkflow challenges understanding. Universe, vast and unyielding, stretches beyond our gazes into endless star and void oceans. Its scales defy comprehension, secrets buried deep in cosmic shadows. Despite all discoveries, one cosmos whisper refuses to fade. Faint but persistent pulls, like invisible tides dragging entire galaxy clusters in single, unyielding directions. This phenomenon is dark flow, challenging not just gravity understanding but reality's fabric itself. In cosmic tapestries, galaxies aren't scattered randomly. They flow, drift, fall toward gravitational wells, invisible dark matter scaffolding and cosmic structures. Most motions can be explained by cosmic expansion driven by dark energy. But in 2008, scientists examining NASA's Wilkinson Microwave Anisotropy Probe, WMAP, data stumbled upon unexpected discoveries. Subtle but measurable galaxy cluster motions all drifting in one direction, like leaves caught in river currents. This wasn't supposed to happen. According to best universe models, galaxy distributions at this scale should be random, movements dictated only by local gravitational influences and gradual space stretching. Yet here was evidence of something more, something pulling entire observable universe regions toward unknown destinations. Discovery sent scientific community ripples. If dark flow was real, it suggested something lurking beyond cosmic horizons, something we cannot see, measure, but can feel. Imagine standing on vast ocean shores, watching waves move not with winds but toward distant points beyond horizons. You cannot see wave causes, but you know something is there, something immense, hidden. How did we measure this drift? Galaxies are unimaginably far away, their motions influenced by countless gravitational tugs and cosmic forces. Scientists turn to Sunyaev-Zeldovich effects, subtle cosmic microwave background radiation distortions caused by hot gas within galaxy clusters. By measuring these tiny distortions, astronomers could infer galaxy cluster motions against Big Bang's faint afterglow. Results were unmistakable. Galaxy clusters spread across billions of light-years were drifting in identical directions at incredible speeds, up to 1,000 kilometers per second. Flows so vast, so consistent, they couldn't be dismissed as statistical noise or observational error. Something massive, something beyond observable universe, seemed to pull these clusters with gravitational fingers we cannot see. Theories began emerging. Some scientists proposed dark flow might be caused by colossal structures beyond observable universe edges, perhaps unimaginably massive superclusters, or even previous universe remnants bleeding into ours. Others speculated it could be extra-dimensional evidence, with gravity leaking through four-dimensional reality's thin boundaries. Then there was the most mind-bending idea. Dark flow might point toward multiverse, collisions between our universe and another, hidden beyond cosmic expansion veils. But here's where things get stranger. Universe, as we understand it, has horizons, limits to observable things. Light can only travel so far in finite universe ages, and beyond those horizons lies nothing we can see. Yet dark flow suggests these horizons aren't reality edges, merely perception edges. This raises profound questions. Are we seeing faint gravitational echoes of something truly colossal beyond our cosmic bubbles? Is our universe just one droplet in endless cosmic seas, each droplet influencing the next in unseen ways? If so, what does that mean for our cosmos places? Are we passengers on drifting ships, carried along by unseen tides toward unknowable destinations? Not everyone agrees on dark flow. Follow-up studies using newer observatories like Planck have questioned evidence strength. Some scientists argue what we're seeing might be artifacts, illusions caused by statistical noise or observational biases. Others remain convinced drifts are real, even if unexplainable yet. Perhaps dark flow's greatest mystery isn't whether it exists but what it represents. If real, dark flow tells us our universe isn't isolated. It's not closed star and galaxy bubbles drifting quietly into voids. Instead, it suggests connections, threads reaching beyond our universe, tied to something larger, older, something we cannot yet comprehend. Think about this. Every galaxy, star, planet, including our own, participates in this motion. We aren't static cosmic observers. We're participants in grand celestial currents, carried along by forces older than time toward destinations hidden beyond light and space limits. Maybe we'll never know answers. Maybe dark flow sources will forever remain veiled behind cosmic horizons. Maybe someday new telescopes, experiments, and theories will allow us to peer just a little further, to glimpse what lies beyond. Until then, dark flow remains gravity-wrapped riddles, hidden in shadows, etched into galaxy motions across billions of light-years. It reminds us how much we still don't know, how small we are, yet how profoundly connected we are to each other, to stars, and to whatever waits beyond universe edges. In the end, dark flow isn't just about galaxy clusters drifting across voids. It's about pulls we all feel toward unknown, unexplored, unanswered. It's about human drives to chase horizons, ask questions, follow faintest cosmos whispers. So we drift, all of us together, carried along by currents we cannot see toward destinations we cannot know. Somewhere beyond light edges, universe holds its breath and waits. Fifth force speculation emerges from labyrinthine universe depths, hidden in intricate particle and force dances. For centuries, physicists built grand cosmic stages supported by four fundamental forces: gravity, electromagnetism, strong and weak nuclear forces. Together they dictate everything behavior, from swirling galaxies above to trembling atoms beneath. Yet despite undeniable success explaining much reality, these four physics pillars leave gaps, questions unanswered, phenomena unexplained. Could there be fifth nature forces? Searches for elusive fifth forces didn't begin with futuristic particle colliders or sophisticated computer simulations. Instead, they began with something older: gravity. At 20th century starts, Albert Einstein shattered gravity understanding with general relativity, revealing it not as traditional forces but as space-time curvature itself. Yet powerful as Einstein's equations are, they coexist uneasily with universe's smallest scales, where quantum mechanics reign supreme. In quantum realms, gravity seems almost out of place, like old acts trying to fit modern plays. Physicists soon realize something troubling. Our best large-scale theories, general relativity, and small-scale ones, quantum mechanics, simply refuse to speak identical languages. In this silence, this chasm between cosmic and quantum, fifth force whispers began emerging. In 2015, deep within Hungary's Atomiki Institute walls, physicist teams led by Attila Krasznahorkai stumbled upon extraordinary discoveries. While studying excited beryllium-8 nucleus decays, they observed unexpected anomalies. Tiny data blips suggesting new particle presence. This particle, if real, could be revolutionary evidence. Force-carrying bosons potentially associated with fifth fundamental forces. They named it X17 particle, hypothetical bosons with masses about 17 mega-electron volts. Its existence, if confirmed, could imply entirely new forces subtly influencing matter in never-before-observed ways. But skepticism runs deep in science. Extraordinary claims require extraordinary evidence. If X17 particles represent fifth forces, what kinds of forces would they be? Some physicists suggest they might act like known-unknown bridges, dark forces interacting primarily with dark matter, mysterious invisible substances comprising about 85% of universe mass. In this scenario, fifth forces wouldn't just change atomic world understanding, they could illuminate cosmology's darkest corners. But implications stretch even further. Fifth forces might explain galaxy rotation curve anomalies, strange gravitational lens discrepancies, or even cosmic expansion drifts. They might unify seemingly disconnected physics threads, stitching together more complete reality tapestries. Yet searches for these forces are fraught with challenges. Atomiki observed anomalies have yet to be independently confirmed, and particles themselves remain stubbornly elusive. Other experiments using tools like Large Hadron Colliders or precision atomic clocks hunt subatomic worlds for ghostly force traces. So far they've found nothing conclusive, but science thrives on unknown edges. Physics history is littered with once outlandish ideas. Space-time curvature, uncertainty principles, light-wave particle duality. Each discovery began with anomalies, faint signals whispering from data depths, inviting scientists to lean closer, question, doubt, explore. If fifth forces truly exist, they could rewrite fundamental nature laws. They might require new mathematics, new experiments, perhaps even new reality thinking ways. But perhaps more importantly, they'd remind us of essential truths. Universe still hides secrets in plain sight waiting for us to notice. For now, fifth forces remain open questions, tantalizing mysteries at science edges. Somewhere in particle collision flickers or distant galaxy dances, answers wait. Whether revealing themselves tomorrow, decades from now, or centuries in futures, one thing is certain. Universe hasn't finished surprising us. It never does. Holographic principle challenges reality perceptions. Imagine everything you know, stars, galaxies, planets, even yourself, isn't quite what it seems. Universe in all infinite beauty and complexity might not be three-dimensional expanse, stretching into infinity, but something far stranger. Something flat, two-dimensional canvas upon which reality projects like light, shining through film onto theatre screens. This isn't science fiction. This is holographic principle, among theoretical physics' most profound and mind-bending ideas. It sits at black holes, string theory, and space-time fabric intersections, and it all starts with unsettling realizations about information and black holes' strange behaviors. To understand how physicists stumbled upon this principle, we need to start at black hole edges. In 1974, physicist Stephen Hawking made groundbreaking discoveries. He showed black holes aren't entirely black. They emit faint radiation, now known as Hawking radiation. Over time, this radiation causes black hole shrinking and eventual evaporation. But discoveries brought troubling paradoxes. What happens to information contained within everything falling into black holes? In our universe, information isn't supposed to disappear. If you burn books, pages might turn to ash, but information, words, ink, letter arrangements, isn't truly destroyed. In principle, you could piece it all back together from smoke, heat, and ash if you had enough knowledge and computing power. This idea is deeply embedded in physics laws. Information cannot be lost. Yet if black holes evaporate completely, where does all that information go? This puzzle is known as black hole information paradox, and for decades it haunted physicists. Among them was Gerard 't Hooft, Dutch theoretical physicist who would win Nobel Prize. In 1990s, as Hooft proposed something radical. Maybe information entering black holes isn't lost. Maybe it's stored on event horizons, black hole boundaries themselves. Imagine three-dimensional objects falling into black holes. Their information, instead of vanishing into singularities, gets encoded on event horizon surfaces like shadows projected onto walls. This realization was profound. It suggested everything happening inside black holes could, in principle, be described by data imprinted on two-dimensional surfaces. But what if this wasn't just true for black holes? What if it was true for entire universes? Enter Leonard Susskind, theoretical physicist who expanded onto Hooft's ideas. Susskind proposed universe itself might operate under similar principles. Everything we perceive in three dimensions might actually be encoded on distant two-dimensional boundaries, cosmic horizons at observable universe edges. Simply put, our three-dimensional reality might be holograms. Before minds start spinning into existential dread, let's clarify meanings. Holographic principle doesn't suggest universes fake or illusory like Matrix. Instead, it proposes fundamental reality descriptions might be simpler than they appear. Vast, seemingly boundless cosmos can be described entirely by information encoded on two-dimensional surfaces. How could this possibly work? How can two-dimensional surfaces describe three-dimensional universes? Think about holographic images. On flat two-dimensional sheet surfaces, you can store information creating three-dimensional illusions. Walk around holograms and you see depth, perspective, even movement. Images aren't in sheets. They're projected from them. Similarly, holographic principle suggests our three-dimensional space experiences, depth, distance, and motion feelings, might be emergent properties of deeper two-dimensional realities. At this point, principle becomes more than curiosities. It becomes powerful mathematical tools. In 1997, physicist Juan Maldacena proposed groundbreaking theories known as AD-CFT correspondence. It provided concrete holographic principle examples in action, showing universes described by three-dimensional gravitational forces could be mathematically equivalent to universes described by two-dimensional quantum mechanics. In other words, gravity and quantum mechanics, two seemingly incompatible theories, might actually be two sides of identical holographic coins. This realization sent shockwaves through theoretical physics. Suddenly, holographic principle wasn't just abstract idea, it was framework, lens through which physicists could attempt to unify modern science's two great pillars, Einstein's general relativity and quantum mechanics. But here's where things get even stranger. If universe is indeed holographic, it raises profound philosophical questions. What does it mean to exist in universes where space and time might not be fundamental? Where everything we see, feel, and experience is, at its core, just information encoded on distant boundaries? It also suggests something deeply unsettling about reality itself. If universe is fundamentally two-dimensional, then space and time, very stages upon which all existence plays out, might not be as solid as we think. They might be emergent properties, like pond-shimmering surfaces, hiding far deeper realities beneath. For now, holographic principle remains theory, tantalizing clue in theory of everything searches. But experiments like those conducted at Fermilab holometers actively try finding evidence for reality's holographic nature. Scientists search for tiny jittering space-time fluctuations, our cosmic screen pixels. Whether or not these experiments succeed, holographic principle has already changed how we think about universe. It's shown us lines between dimensions, between space and information, might not be as clear as once believed. It's reminder that reality, no matter how familiar it feels, still holds secrets so strange they seem pulled from science fiction. So next time you look up at night skies filled with distant stars and galaxies scattered across unimaginable distances, remember this. It's possible everything you see exists not in three-dimensional space stretching to infinity, but as information encoded on reality's edge. Cosmic hologram of breathtaking complexity and beauty, projected from universe's two-dimensional boundary into three-dimensional experience we call home. For now, we can only marvel at possibility, wonder at implications, and continue searching for truth about reality's nature. Perhaps universe is hologram, Perhaps not. But in asking question, in pushing understanding boundaries, we participate in humanity's greatest adventure, quest to understand cosmos and our place within it. In this story's end, whether universe is holographic or not, one thing remains certain. Reality is far stranger and more wonderful than we ever dared imagine. And somewhere, in equations yet to be written, or in observations waiting to be made, truth about universe's nature patiently waits, ready to reveal itself when we're ready to see. The heat death of the universe represents the ultimate conclusion to the greatest story ever told. The cosmic narrative that began with the Big Bang and will end not with catastrophic destruction, but with a gradual, inexorable fade into eternal silence. This scenario, first conceived by 19th century thermodynamicists and refined by generations of physicists and cosmologists, presents us with a future so distant and so final that it challenges our very conception of what it means for something to exist. Today, our universe feels vibrantly alive. Stars burn with the fierce intensity of nuclear fusion, converting hydrogen into helium and releasing the energy that illuminates galaxies across hundreds of billions of light years. Planets orbit their parent stars in gravitational dances that have persisted for billions of years. Galaxies themselves spiral through space in grand, sweeping arcs, their hundreds of billions of member stars following orbital paths that will carry them around galactic centers for hundreds of millions of years to come. From the smallest scales to the largest, energy flows in continuous streams. Electrons cascade between atomic orbitals, molecules vibrate and rotate with thermal energy. Chemical reactions drive the metabolism of living organisms. Winds and ocean currents redistribute heat around planetary surfaces. Solar radiation travels across interplanetary space, and stellar winds carry charged particles throughout solar systems. Motion is everywhere. Change is constant, and time marches forward with apparent purpose and direction. But according to our best understanding of fundamental physics, this dynamic, energetic era of cosmic history is temporary. A brief, brilliant interlude in a much longer story that will eventually conclude with absolute stillness. One day, in a future so distant that it dwarfs the current age of the universe by factors of trillions upon trillions, every star will flicker out, every planet will freeze, every black hole will evaporate, and every trace of motion and energy will fade into uniform, unchanging silence. This is the heat death of the universe, not a violent explosion or sudden catastrophe, but the inevitable consequence of the most fundamental law in all of physics, the second law of thermodynamics. To understand how the dynamic cosmos we observe today could possibly wind down into eternal frozen stillness, we must first understand the profound concept of entropy and its role in determining the ultimate fate of everything that exists. The story of entropy begins in the mid-19th century with the work of Rudolf Clausius, a German physicist and mathematician who was trying to understand the theoretical limits of steam engines and other heat-powered machines. Clausius realized that there was something special about the direction in which heat flows. It always moves from hot objects to cold objects, never the reverse, unless external work is performed to force it backward. This insight led Clausius to formulate a new quantity he called entropy, derived from the Greek word for transformation. Entropy measures, in a precise mathematical sense, the degree of disorder or randomness in a physical system. More fundamentally, it quantifies the number of different microscopic arrangements of particles that are consistent with the macroscopic properties we can observe. Consider a simple example: a cup of hot coffee sitting in a cool room. The coffee has low entropy because its thermal energy is concentrated in a relatively small volume, creating a highly organized state where fast-moving molecules are confined to the liquid while slower-moving air molecules surround it. But this organization is unstable. Heat begins to flow from the coffee to the surrounding air through conduction, convection, and radiation. As time passes, the coffee's thermal energy spreads throughout the room. The coffee molecules slow down while the air molecules speed up, until eventually the entire system reaches thermal equilibrium at some intermediate temperature. This final state has much higher entropy than the initial state, because the energy is now distributed uniformly rather than concentrated, and there are vastly more microscopic arrangements of molecular velocities that are consistent with this uniform temperature distribution. Crucially, this process is irreversible. Once thermal equilibrium is reached, the system will remain there forever unless energy is added from outside. The coffee will never spontaneously return to its original hot state by extracting thermal energy from the now slightly warmed air. Such a process wouldn't violate conservation of energy. The total amount of energy would remain constant, but it would violate the second law of thermodynamics by decreasing entropy. Ludwig Boltzmann, an Austrian physicist working in the late 19th century, provided the statistical mechanical foundation for understanding entropy. Boltzmann showed that entropy is fundamentally related to probability. High entropy states are simply much more probable than low entropy states, because there are vastly more ways to arrange particles in disordered configurations than in ordered ones. Imagine dumping a box of numbered balls onto the floor. There's exactly one arrangement that would place them in perfect numerical order, but there are countless arrangements that would look random and disordered. If you shake the box and dump the balls repeatedly, you'll virtually always get a disordered arrangement simply because disordered arrangements are overwhelmingly more probable. Similarly, isolated physical systems naturally evolve toward higher entropy states because those states are statistically favored. The universe as a whole is the ultimate isolated system. By definition, there's nothing outside it that could add or remove energy. Therefore, the second law of thermodynamics tells us that the universe's total entropy must always increase, or, at best, remain constant. This has profound implications for the cosmos's ultimate fate. Currently, our universe exists in a state of incredibly low entropy compared to what's theoretically possible. This might seem counterintuitive given the apparent chaos and complexity we observe, but the key is understanding that gravitational systems behave very differently from ordinary thermodynamic systems. In most of the universe, matter exists in highly organized structures. Stars burn steadily for billions of years, planets maintain stable orbits, and galaxies persist as coherent entities for cosmological timescales. This organization exists because gravity can create and maintain structures that would be impossible in other contexts. When gas clouds collapse under their own gravity to form stars, the gravitational potential energy released during collapse heats the gas to temperatures sufficient for nuclear fusion. The resulting star can burn steadily for millions or billions of years, converting nuclear potential energy into heat and light while maintaining a delicate balance between gravitational collapse and radiation pressure. But this process cannot continue forever. Every fusion reaction that occurs in a star's core irreversibly converts some mass into energy, slowly depleting the star's nuclear fuel. When the fuel runs out, the star must either collapse further or exhaust its ability to generate the radiation pressure needed to support itself against gravity. Either way, the star's long period of stable energy production comes to an end. The timeline for stellar death depends critically on mass. The most massive stars burn their fuel quickly and explosively, ending their lives as supernovas within just a few million years. Medium-mass stars like our Sun burn more moderately and will eventually expand into red giants before shedding their outer layers and leaving behind white dwarf remnants. The least massive stars, red dwarfs containing less than about half our Sun's mass, burn their fuel so slowly that they can continue shining for hundreds of billions or even trillions of years. But even red dwarfs are not eternal. In approximately 100 trillion years, a timescale roughly 10,000 times longer than the current age of the universe, the last red dwarf stars will finally exhaust their nuclear fuel and fade into darkness. When that happens, the stelliferous era of cosmic history will come to an end, and the universe will enter what cosmologists call the degenerate era. During the degenerate era, the universe will be dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects are the corpses of former stars, containing most of their progenitors' mass, but no longer capable of generating energy through nuclear fusion. White dwarfs will slowly radiate away their residual thermal energy over timescales of quadrillions of years, gradually cooling until they become cold, dark objects sometimes called black dwarfs. Neutron stars, the ultra-dense remnants of massive stars that didn't quite become black holes, will also slowly cool through neutrino emission and other processes. Some neutron stars might eventually collapse into black holes if they accrete enough additional matter, while others will remain as inert dark objects for unimaginable periods of time. Black holes themselves will persist much longer than any other objects in the universe, but even they are not truly eternal. In 1974, Stephen Hawking made the remarkable discovery that black holes emit a form of thermal radiation, now known as Hawking radiation. This radiation arises from quantum mechanical effects near the black hole's event horizon, where pairs of virtual particles are created from the vacuum energy of empty space. Normally, these virtual particle pairs would immediately annihilate each other and disappear back into the quantum vacuum. But near a black hole's event horizon, it's possible for one member of a virtual pair to fall into the black hole while the other escapes to infinity. From the perspective of a distant observer, this appears as though the black hole is emitting particles and slowly losing mass in the process. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes are actually hotter than larger ones. For a black hole with the mass of our Sun, the Hawking temperature would be only about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that currently fills the universe. Such a black hole would actually gain mass by absorbing background radiation faster than it loses mass through Hawking radiation. But as the universe continues to expand and cool, the background radiation temperature will eventually drop below the Hawking temperature of even the most massive black holes. When that happens, black holes will begin to evaporate, with smaller ones disappearing first and larger ones following over increasingly long timescales. The evaporation time for a black hole is proportional to the cube of its mass, leading to enormously long lifetimes for the supermassive black holes found at galaxy centers. A black hole with 1 billion solar masses, typical of those found in large galaxies, would take approximately 1,000 years to evaporate completely through Hawking radiation. This number is so large that it's difficult to comprehend. It's longer than the current age of the universe by a factor of 10 to the 90, meaning that if you wrote out the evaporation time in years, it would require more digits than there are atoms in the observable universe. When the last black hole finally evaporates in the unimaginably distant future, the universe will enter what some cosmologists call the photon era. At this point, space will contain only elementary particles, photons, neutrinos, electrons, positrons, and perhaps protons if they turn out to be stable. These particles will be spread so thinly through space and moving so slowly due to cosmic expansion that interactions between them will become extraordinarily rare. But even this may not represent the ultimate fate of matter. Some theories in particle physics predict that protons themselves are unstable and will eventually decay into lighter particles like positrons, neutrinos, and photons. If protons do decay, the predicted lifetime is enormous, at least 1034 years and possibly much longer, but finite nonetheless. If proton decay occurs, then even atomic nuclei will eventually disintegrate, leaving behind only leptons, photons, and neutrinos. The electrons and positrons will occasionally encounter each other and annihilate, producing more photons. Eventually, the universe might contain nothing but an extremely dilute gas of photons and neutrinos, all redshifted to incredibly long wavelengths by billions of eons of cosmic expansion. At this point, the universe will have reached a state of maximum entropy, what physicists call thermal equilibrium. Every bit of energy that was once concentrated in stars, planets, and living organisms will have been spread uniformly throughout space. There will be no temperature gradients to drive heat engines, no chemical gradients to power reactions, no gravitational gradients to enable the formation of structure. In such a universe, time itself loses its meaning in any practical sense. Time as we understand it is intimately connected to change. We measure time by observing processes that evolve from one state to another. But in a universe at maximum entropy, no processes occur because every possible reaction is exactly balanced by its reverse reaction. Past, present, and future become meaningless concepts because nothing ever changes. This scenario, the heat death of the universe, represents the ultimate triumph of the second law of thermodynamics on cosmological scales. It's a future where entropy has increased to its maximum possible value, where energy has been diluted beyond any possibility of useful work, and where the dynamic, evolving cosmos we observe today has settled into eternal, changeless equilibrium. Yet there's a strange beauty to this seemingly grim fate. For billions of years before heat death arrives, stars will continue to burn, planets will continue to orbit, and the universe will remain filled with light, motion, and possibility. During this cosmic golden age, which includes the present era, the universe will give rise to structures of breathtaking complexity. Galaxies, solar systems, planets with dynamic atmospheres and climates, and perhaps countless forms of life and intelligence. The knowledge that this era of cosmic fertility is temporary doesn't diminish its significance. If anything, it makes it more precious. Every star that shines, every planet that harbors life, every moment of consciousness that contemplates the cosmos represents a temporary victory of order over chaos, of complexity over simplicity, of information over randomness. And perhaps, in ways we can't yet imagine, intelligence itself might find methods to delay or even reverse the approach of heat death. Advanced civilizations of the far future might discover how to extract energy from quantum vacuum fluctuations, manipulate the expansion of space itself, or access energy sources that we haven't yet conceived. The laws of thermodynamics might prove to have loopholes that become apparent only when intelligence reaches levels of sophistication far beyond our current capabilities. Even if heat death is inevitable, the timescales involved are so enormous that they dwarf any conceivable measure of human experience or concern. The universe has at least 1,000 years of active history ahead of it before entropy finally wins, enough time for countless cycles of stellar birth and death, for the emergence and extinction of billions of forms of life, for achievements and discoveries that we can hardly begin to imagine. In the end, the heat death of the universe will not be a dramatic conclusion, but a gradual fading. The universe's story ending not with a bang, but with the softest possible whisper. It will be the final period at the end of the longest sentence ever written, the closing note of a symphony that began with the Big Bang and played for longer than any human language has words to express. But that ending lies so far in the future that it might as well be infinite from our perspective. For now we exist in the universe's youth, surrounded by burning stars and swirling galaxies, living in an era when entropy is still low enough for complexity to flourish and consciousness to ponder its own existence. We are temporary arrangements of matter and energy, brief eddies of organization in the cosmos's long flow toward equilibrium. But we are here, we are aware, and we can marvel at the extraordinary story of which we form such a small but meaningful part.